Actually walk you through why we did what we did, the exact use case behind it, how we move data today within Yahoo, and then we'll talk about what this new feature does and why we actually did this. Chris will also demo the particular feature of Hive. Okay. Okay, so this is an attempt, actually, to describe how we move data in and out of clusters today. So there are lots of components here, but the interesting thing is, so at the center of this picture is the cloud picture, so that's the multi-tenant cluster, the Hadoop cluster. And of course, the cluster is where the data knows file or HDFS is, and in certain cases, when we move data out, we use macros, in certain cases we don't, right? So the options are many. Most of our customers of the big data platform, which is typically in our case, come to the clusters via what we call as launchers or gateways. They are just those machines. They're pretty similar, except that launcher is something which we say is in the client for customers control. So they access via SSH, and again, when you talk to HDFS, it's the ODBC today. Right? The other popular ways to access data, both for in and out, particularly for out, is HDFSProxy. That's also on your left side, second box. It's just yet another proxy server. And I've just shown one box, but if the load is such that we need multiple boxes, we can put a load balancer and add boxes. And this is the one that sort of redirects the request, streams data out to the request. And then HDFSProxy is again a standard of proxy. In our case, we used to use YPS or ADS Apache traffic server, and we have now moved to the next generation technology. That's not open source, it's probably enough. So those are the three popular mechanisms through which people access the clusters, move data out of the clusters, right? Once you're done with your MapReduce jobs, you want your results out, typically, to do further downstream processing or analytics or whatever the case may be, warehousing. On the rightmost side, we have something called as grid data management. It's a custom tool that we have built for managing the data lifecycle. And when I say lifecycle, it's all the way from acquisition to retention, replication, and all of that good stuff. It also uses for the data movement a proxy server. It's a custom proxy, not a load proxy, but nothing special about that. Most of these proxies are in context servers. There's some logging, some instrumentation, and then of course the HDFS, the file system APIs. And the various sort of ways you move data. And this is yet another tool for intra-cluster, so that's another example of how we move data between clusters. Okay? So that's what happens today when it comes to sort of moving data out of the clusters. Those are the mechanisms available, and those are the most popular ones we use today. So this is just to illustrate a typical scenario for data out. The data is typically stored in predefined directory locations on HDFS, where you want to pull that data out from, right? As files, essentially. And the clients determine, through some custom interface, that they now need to go pull that data. It's also available for committed, right? The feeds are committed, ready for consumption, downstream consumption. And if they figure out that, yeah, the feed is committed, that's something that I can now consume, they get a list of files that they want to pull out of the directory, and then pull those files one by one, typically using HDFSProxy. HDFSProxy is very similar to Hoop, if you've heard of that. Or in 2.0, I think they call it HDFS, something, I think I have a name. We don't use it yet. HTTPFS gateway. That's the name given to it. But it's the same. It's all the same. They're all coordinated inspired by HDFSProxy. So that's a typical scenario, as you see. You figure out where to sort of pull the data from HDFS. Via HDFSProxy, you temporarily store it in a file for a variety of reasons, and then you can use Oracle SQL loader. Let's say in this case, you want to put it in an Oracle database. Or if it's data in the files, you can use external tables directly to put it back in the fact tables. And insert it back in the fact tables. So that's how you're putting data out for a particular situation where I want to store those results in an Oracle database. Okay, so there are some good things about doing these, and there are some bad things about doing this. That's the good things all around, I would say, security and performance. One rule we follow is that we don't store database passwords on videos. Right? We just don't want to take that security risk. Compression is quite important, particularly when you're flying across Colo or moving data across Colo, across data centers. Network bandwidth is quite expensive. And in certain cases, it's not possible for us to move compressed data, and we want to move compressed data. Encryption is yet another issue, because whenever we're sort of in a situation where we think the traffic may get routed, which is not in our control, we want that data to be encrypted. And then ACCOs for access control. We don't let the database hosts access the data nodes directly. They almost always go to a proxy for access control reasons. The cons are many, as you saw, right? You need to understand the directory structure. Data discovery is a challenge. Like you need to understand when the feed is committed, when should I go pull that. Maybe, let's say you have a predetermined tool of like you determine every hour my feeds will be available for consumption. I'll go read it from a particular directory location. It may or may not be. Let's say the pipeline's running late, that's processing the data, and the data is not ready for consumption. What do? You keep pulling or retry. Then it also uses what we call a dump files, right, which is a marker. Okay, now it's done, go pull it. And then maintenance also is an issue because this forces you to maintain separate schema files and schema file formats, your own sort of schema. Because you don't know. Only the person who has written this application and is consuming the data of the custom knows what the schema for the file is. So those are the bad things. So how do you solve this? So we have, for a long time, had this issue, and luckily, sort of HCatalog came along, and we kind of went that route, using HCatalog as a central metadata system for Hadoop. So HCatalog addresses a lot of that, but when we introduced HCatalog, the successful use case came up, which is what we call as HCatalog or Hive data. Now, by the way, it's merged as a single project. So it's all Hive, perhaps going forward. So we'll talk about that. That's what this particular talk is about. But I just wanted to give you guys the context of why we did what we did. So HCatalog, this is a picture from Al Gates from last Hadoop Summit. And it just shows that Hadoop is sort of one platform. Let's say in our case, we call it the cloud platform for processing big data. And it has many tools. Some of those tools are MapReduce, which is good at certain things. Yet another tool came along, which was Hive, which is good at certain things, right? So BI analytics type use cases. And as you can see, if someone's using Pig and the other person's using Hive, they're not typically sharing data. So that was one of the big problems why HCAT was introduced to allow the sharing of data. And then it actually has a bunch of other nice properties that we'll walk through. But essentially what HCatalog does is that it opens up the Hive metastore for everybody else, all the other tools in the ecosystem, like paper MapReduce. So they can all share the schema that's defined in the metastore. That's what Hive does. So it sort of leverages that concept, both for MapReduce and Cake. So those are the arrows. They all kind of go into the common metastore trying to access the same metastore that can then provide the tabular abstraction There's yet another nice property that all of that now goes through a SCSI or serializer and deserializer. What that does is that it abstracts out the data format, the underlying storage format of the files for the user. So you need not worry about what the input format was or the output format. It kind of abstracts it for you. So those are the properties that I just walk you through. The HCatalog's core value proposition, right? Allows for interoperability, sharing of data. It provides the abstraction, there is abstraction in terms of tables and schemas. And the way it works is that you define a database table and then partitions. Maybe perhaps in another talk we can walk you through the details of HCatalog, but that's not the purpose of this talk yet. It also supports nice things like schema, which you can add columns and stuff in the predefined schema. And then that's the last point that I was talking about when I talked about SCSI, is that it abstracts out the storage format. Okay, so we talked about data out and the ways we pull data, right? Then we talked about we introduced HCatalog as the mechanism for maintaining metadata, so maintaining and retaining metadata centrally, right, in our Hadoop clusters. And so what people said was, well, we were now, we were earlier, when there was no HCatalog, forced to know the file location, the schemas, we were maintaining all of that ourselves. We were also figuring out where to go pull the data. Now that we have HCatalog, you should provide me a way to pull the data out without me doing any of that. Right? I don't need to know about those things anymore. I don't need to know when it's coming and when it's not. Give me a notification so that I can go pull the data. And I don't want to pull the data anymore with files by file or even understand the location of the file, given that I have HCatalog. Right? So it's now, I know the tables, I know my schema, I get a notice, I go pull that. I will show you how we do that. Okay? And one of the interesting things we did was right around that time when the use case became prominent for us, Hive Server 2 was under development. So we picked Hive Server 2 and the ODBC interface that it provides went through a revamp, and Chris will actually walk you through some issues with the Hive Server and how Hive Server consists of those. So it has lots of nice properties for which we were able to provide containers with the IQ sessions directly to the data sitting on the grid so that people can visualize the results. And the JDBC interface was what we used to pull this feature off, which was data. So that's sort of the Hive server side. And on the HCatalog side, it has notification support, so we started sending any consumer of those notifications can consume it. We in fact have a recipe system. I see our president here, voice line, and the cloud messaging system. So we actually leverage that, and it's supposed to have active and queue. So those notifications actually trigger the event that then allows the clients to start consuming the data. With that, and then of course these issues that I just talked about kind of got solved with the scheme of things, right? So with that, I'm actually going to invite Chris. Chris Stroh is the Hive development lead who worked on this project and is also the member of this division.
Hello. Can everyone hear me? Great. So thank you, Sumit, for doing the introduction to this. And I'd like to just continue on from what he was saying by picking up and reviewing some of the points that he already mentioned. So there are many open source and proprietary methods for loading and managing data on the grid already. An example of that would include Scoop, which just so happens to be doing a presentation tonight as well, so you might want to stick around and learn a little bit more about that technology. By contrast, though, there are fewer ways of effectively getting data off of the grid, and this can be further complicated by the underlying storage format of the data. So to illustrate this point, you might want to consider a sequence file or an RC file. You can easily copy this file off of the grid onto a local box for processing. the data isn't readily available to you unless you complete additional processing in order to extract the actual values from the file. So another challenge or another consideration is the amount of data, or the size of the data that you're trying to transfer off of the grid. So in many cases, this tends to be large enough that traditional methods or conventional methods are just not practical anymore. So with data out, we designed it to try to address a lot of these issues. The system builds upon some of the more recent developments in the Hive community by leveraging some of the work that has been done around the Hive Server 2 project. So for those of you who may not be familiar, Hive Server 2 is a complete redesign of Hive Server, which addresses various design issues that were found in the original version of Hive Server. So it's deployed as a server, and it accepts connections from JDBC, ODBC, and Thrift-based clients. In addition, it also has functionality that manages concurrent client sessions, and it executes HiveQL queries on the underlying Hive tables and the metastore. So what is data out? Data is an API that exposes methods for efficiently or effectively moving data off of the grid from within these Hive tables. The API extends the Hive Server 2 JDBC driver code, and as a result, anyone who has worked with JDBC API in the past should be fairly comfortable using the data out API as well. So data out works, as Sumit mentioned, data out works with HCatalog to retrieve data that is managed by Hive and stored in Hive tables on the grid. So in this way, it's agnostic to the storage methods or the storage formats that are being used to store the data on the grid. In addition, it provides methods or functionality that allows you to pull individual or smaller portions of the whole data set in parallel. So finally, because it's an API, it is readily embeddable, or it's easily embeddable within existing applications, and there are absolutely no restrictions with how the data can be used. So what I mean by this is that the data can be pulled off of the grid, and it can be written into a file in the local file system, or it can be inserted directly into a database, or it can be even streamed to another application within the context of a larger processing pipeline. So currently, with our deployment of data, we are restricting queries, fetch queries, to the type that is shown here, where it's select star from queries. But we are actively working on adding support or functionality to support just an arbitrary set of queries. And we expect to finish that in the very near future. So this slide illustrates how data was deployed in Yahoo as a pilot service. So the service consists of a small cluster of Hive Server 2 instances that are responsible for performing the work of executing the query and then returning the data associated with that query back to the client application. So notice the distinction here between the HS2 instances. Those instances which are responsible for processing and executing the query are colored in blue, while those that are responsible for returning the data back to the client application are colored in orange. So we've decided to go with this kind of distinction when we deploy this as a system, but there's absolutely no requirement that says you have to work this way. In fact, you could deploy a single instance of Hive Server 2 and use that to process queries as well as retrieve the data that's associated with the underlying result set. So I won't really go into too much detail why we made this decision. Finally, you have the client machine, which, or machines, depending on the case, which runs the application that embeds the data out of libraries. So let's dig a little bit deeper into how this is actually working. So this slide shows how data out actually works. Again, the processes here have been color coordinated so that they correspond with the HS2 instance that it would actually connect to, that I introduced in the previous slide. So here we see a master process designated by M, which submits a query for execution to the Hive Server 2. And it requests not the actual data for that query, but it actually requests the Hive split objects that are associated with those results. So as I mentioned, instead of returning the actual data to the master process, the Hive server will generate a list of Hive splits that correspond with the underlying data. So what is a Hive split? A Hive split is just basically an abstract representation of some smaller portion of the whole data set. So you can see here that each of the Hive splits that we received can then be farmed out to separate slave processes designated by the S processes. And those slave processes are then responsible for fetching the actual data from the Hive server 2. So it should be noted in this way, we can actually pull down all of the data that is associated with the result set in parallel, where each of the S processes is responsible for actually retrieving just some small portion of the total data set. And again, there's no reason why all of these requests have to be served by a single Hive Server 2 instance. So the load can be distributed across all of the instances that make up your small cluster out there. So I'll move on to a little bit of code right now. So this shows some demo code that uses the data out API. And for anyone who has worked with JDBC API before, this should be pretty familiar to you. So this code here would be equivalent of what would run on the M process. So we see at the top how the data out is used to create a Hive connection object. Using that Hive connection object, we call the create and generate split statement to create a new statement object, which we then use to execute a Hive query, a Hive QL query. So the while block then iterates over each of the individual Hive splits and launches a new job to fetch the data that is associated with that split. So note here that you have to synchronize on the fetch jobs. So the reason for this is that the server-side resources are associated with the connection, or rather the session that launched the initial request or launched the initial query. So that process has to synchronize with the other processes that are retrieving the data before it can close its own resources. So this code here would correspond with code that would run on the S process in the previous slide. Again, we would start by creating a new Hive connection that would establish a connection with the Hive server. That would be followed by creating a prepared statement by using the prepare fetch statement, split statement on a specific instance of a Hive split object. So by calling the execute query on the prepared statement, it will generate a result set that you would then use to access the actual metadata or the actual data that is associated with that particular split. So again, the Hive split creates a very clear boundary around the data that you can actually access, so it's not going to spill over into other areas. So here, the while loop, again, would step over each of the rows, and you would process the individual column values before closing all of your remaining resources. And then you'd finally communicate your status back to the master process. And you can imagine that this would be running in parallel across multiple machines. So this is the essence of the code that I'll show you actually running in a demo now, assuming that the demo works properly. So I'll log into a cluster, and I'll run the demo. Unfortunately, I seem to have lost a little bit of the input, but I'll tell you what happened. The first block of output that you would have seen shows the tables that were being managed by this Hive server. So this is just very basic JDBC functionality that you inherit by using data out. It's not particularly associated with data out in any way. So from that table, or from that listing of tables, you would have seen that there's a job info table which we want to run a query on. And that query was a select star from job info where cluster is equal to AB or cluster is equal to CB. So effectively we're pulling data that we've mined from two of our different clusters. What you see at the very top of this screen are the three Hive splits that were returned to us. So the first one happens to correspond with data from the AB cluster, and that's what we're going to actually fetch. So you can see here that it's starting to fetch the split data. It produces an output by fetching the metadata that's associated with that Hive split. So you can see all the individual columns and the data types that are associated with those columns. So it goes and fetches this data, and you see one dot being printed for every 10,000 rows of data that were successfully downloaded from the Hive server 2. So we get through and successfully retrieves 207,000 rows, which amount to 24 MB worth of data. So this is formatted, and we decided to write it into a file on the local file system, which I'll open up for you. So this is the file that was written for us. It's just formatted as a tab-separated file where we have all the individual values corresponding to the set of columns that you saw. Okay, so now I'll go back to the presentation. So before we actually did any work on building out the functionality for data, we ran some performance numbers or performance tests on Hive Server 2 to roughly see whether we could achieve the objectives that we wanted. So you can see this is some baseline statistics that were collected on Hive Server 2 with only a single client server streaming data from Hive Server 2. So we gathered performance numbers for a variety of fetch sizes as it streamed different amounts of data through Hive Server 2. And what you can take away from this is that the throughput time or the transfer time increases linearly with the amount of data that we're retrieving. And also the API provides a method for actually tuning the fetch behavior according to the characteristics of the underlying data set. So in our case, we actually found sort of a sweet spot of between a fetch size of around 100 and 500 rows, which consistently give us good performance results. So this slide displays similar performance numbers except this time we've increased the number of concurrent connections to 5 clients who are streaming data simultaneously from Hive Server 2. So again, the points that we can take away are very similar. We have a linear increase that is proportional to the amount of data that we're pulling out. And again, we see that with a fetch size set around 100 to 500, we consistently get good performance with throughput. So you may notice that by comparison to the baseline numbers, the transfer time has increased, but I think that's fairly reasonable. And in this particular case, we see that increasing the number of concurrent client connections by a factor of 5